Hi, today we will be looking at the step response of the RL circuit, specifically the discharging behavior. So, our circuit looks like this. In this case, we will assume that our voltage source has been switched on for a long time so that my inductor has had enough time to completely charge. And then we're going to switch off the source, and then we're going to see what happens. In this case, the behavior of our current in the inductor is IL of t equals V in over R times E to the minus t over tau. And tau again is, like in the previous video, L over R. So that is the discharging behavior in the current. We can also calculate what the voltage will look like, because we know that the voltage in the inductor is equal L times the first derivative of the current. So my voltage is L times the first derivative of V in times E to the minus t over tau, which is, V in over R, which is this equation here. I just plug it in here. And since V in and R are constant, they can come out. So I have V with the L. So L over R times the input voltage times the derivative of my exponential. And the derivative of my exponential is my exponential times the derivative of the exponent. And the derivative of the exponent with respect to t in this case is minus 1 over tau. So my voltage ends up being L over also minus 1 over tau times L over R times times VI. I'm going to put the VI here, times my exponent. So substituting tau by L over R, we get the inverse of L over R is R over L, so minus R over L times L over R times V in times E to the minus t over tau. So these two go away with these two, and our voltage is minus VI times E to the minus t over tau. So how does this look like when we look at it in a graph, in a time domain graph? So I'm going to put that here. That's not very straight. Here. So because we already have also we know already the charging behavior, I'm going to put both of them here now. No, I'm going to start first with the discharging behavior. So our input voltage would have been on for a very long time beforehand, and then at t equals 0, we switch our source off. So my input voltage looks like this. And then the current in my inductor, which will be described by this equation, the current in my inductor, because the inductor will have been charged for a very long time, it will have a high current, it will be charged. And then as the source switches off, it will start to discharge in this manner until we get to 5 tau, about here. Now, likewise, the voltage will look like this. The voltage will be 0 for a very, very long time because it was charged, it's been charged. And, remember from the previous video, we saw that the voltage on the charged inductor is equal to 0. And then suddenly at V at t equals 0, we will have a negative voltage here, and then it will go back down, go up to 0, and that's not a very nice curve here. So it will do like this, and that's somehow not the right rate. Like this, more or less. So now, why do we have here a negative voltage suddenly? I can show you with a circuit, because so this is the current. So when we switch off the source, we basically have here a short circuit. And suddenly, I'm going to have current from the inductor flowing in this direction. But we are measuring this voltage. So since we're measuring this voltage and our current goes in the opposite direction, therefore we get a negative voltage here. And the negative voltage that we get here is V in. And in the case of the current here, this is V in over R. So our input voltage over R. So this is how our discharge plot looks like. And now I would like to show you how it looks like when we have both charging and discharging behavior the same, one after the other, like we did previously with our capacitor circuit, with our RC circuit. So putting them both together, if we have our input voltage that's first 0 for a long time, and then it switches on, and then after some time it switches back off again, then I will have my charging behavior here, my discharging behavior there. So my current in my inductor will be 0 as long as it's been discharged for a long time. Then it charges slowly, more or less, up to 5 tau, assuming that in my time axis here I let it charge to 5 tau. So I have my charging behavior here, and then when the source is switched off, then it discharges slowly like this. And let's assume that in this case we have then 10 tau at around here. I'm going to put my time axis a bit longer. Time axis. So that would be how my current behaves, and my voltage will be 1, so V in, for as long as it's charged, and then, if it's switched off, it's been discharged for a long time, so yeah, it starts with 0, and then at t equals 0, it jumps up to V in here, and then it drops back down to 0. And when the the source switches, it jumps back to minus V in. So I'm going to put here minus the input voltage, and then it will go back down to 0, more or less like this. So that in the current here, my current here would be V in over R, which is my maximum current, and the voltage will be like that. So one very important thing to take out of this graph is the following. If we look at the current and we look at every point, any arbitrary point along the curve, and we compare that point with one instant before that point and one instant after that point, those 3 points are always very close together. Yeah, so that means that there are no sudden jumps in current in my inductor, never ever. So my inductor manages to smooth out any changes that happen in the circuit. The current, the inductor smooths those changes in the current. However, at the expense that the voltage changes suddenly. Whenever my voltage source changes, my voltage changes suddenly. So yeah, that's it for the step response of the RC/RL circuit. And on the next videos, we will be looking at the frequency response and how to deal with such a circuit when we have a sinusoidal input instead of a DC input. Thanks for watching.